And see my Okay, cool. Well, I can introduce myself too quickly. My name is Audrey. I'm a PhD student at Stanford working with Adam Brandt on methane measurement technologies and controlled release testing. And today I'll be talking about my master's project, which was a controlled release test of a wide variety of methane measurement technology at the TADI facility. And TADI stands for TotalEnergies Anomalies Detection Initiatives, which is very long. So be referring to it as TADI. Um, so I'm going to talk a little bit about the background and motivation for this project, and then give you some information about the teams that are participating or that were participating. And then we'll go through the experimental methods, talk about the results, and then hopefully have some time for discussion at the end. And so I don't think I really need to tell this crew, but always important to talk about like the advances globally in methane emission measurement and regulation. And one of the strongest methane regulations, if not the strongest ever, I think, is being implemented right now in the EU methane regulation. And they're increasing standards for monitoring and reporting, and also the advances of new technologies that unlock the global monitoring and satellites and remote sensing advances. And so, with its methane rules, the EU has established itself as probably the global leader in methane regulation, specifically as it pertains to the energy sector. So, primarily oil, gas, and coal production. And in only 1 year, in 2027, the measurement, monitoring, reporting, and verification practices of all of the energy companies active in the EU must be up to standard, which essentially means OGMP 2.0 reporting requirements. And this really raises the stakes for methane measurement technology, especially within the EU and for European companies. So, accurate data is like the foundation of effective climate action. And as all of these regulations tighten, the need for verified and reliable measurement technologies is becoming critical. And so, independent and blinded controlled release testing is kind of the key to building the trust in these measurement technology, both for detection and quantification ability. Um, and over the past decade, the Environmental Assessment and Optimization Lab at Stanford has spearheaded some of these large scale comprehensive blind testing. I'm sure we've heard from this group about it before. This lab has been doing this for many years, from way before my time at Stanford. Sahar was extensively involved, and we published a lot on the results. And recently, our focus has been on high emission rate releases for the testing of satellites. Um, and expanding our controlled release experiments globally, including in the EU. So, controlled release experiments and intercomparison studies have been used to improve and evaluate the performance of methane emission measurement systems with a wide variety of results. And different studies propose different conclusions that strongly depend on like the specific experimental setup of those experiments, whether they were like mobile or fixed platforms tested, what are the sensors, what are the sampling strategies, what are the models they were using. And with the regular improvement of instruments and techniques, we believe that these new intercomparisons based on controlled releases and involving a wide range of technologies are needed periodically. And are some example results from Liu et al., which is one of the most recent controlled release studies published in 2024 with experiments in 2021, and was one of the first to focus exclusively on mature technologies that are available in Europe. And you might be asking, why do you need to do another controlled release study if this one was just published? And we believe that there are benefits to each additional experiments and studies, because even if the experimental setups were exactly the same, the technologies could have changed significantly in the 3 years between experiments. However, there are some main differences between, for example, this study and the one that we conducted at TADI, including the fact that all of our results are made public and are not anonymized, which we think is important to move toward general consensus on these technologies. And also, the release rates included in this experiment were 50 kilograms per hour or lower, while the experiment I'll talk to you about today included higher volume emission rates, which is especially important when we think about the application of these measurement systems to super emitter events. So we tested 13 different measurement systems over 4 weeks in June and July, or sorry, June and September of 2024. There were broadly 5 different technology groups: drones, satellites, vehicles, aircraft, and fixed sensors. These teams came from both commercial entities and research labs, so academic groups from all across Europe. And some of the academic groups formed kind of like a mega team um, with collaboration between different research entities. And the teams came from all over Europe and with some US and Canadian presence as well. To talk about the drone teams quickly, we had 4 drone teams. We actually had 5 drone participants scheduled, but one of them crashed during one of the first releases they were measuring, and so they could not participate in the rest of the testing. And they were all commercial operators, and they all had similar measurement techniques with in situ concentration sensors on the drones and flew downwind transects once identifying the plume and the wind direction. We also had 3 fixed ground sensors teams, and a lot of times these are referred to as continuous monitoring teams. But in our experiment, the release periods were known, so we weren't really testing the ability to monitor continuously. So we refer to them as our fixed ground sensors, kind of in contrast to mobile ground sensors, which are like vehicles. And these were also all like what we refer to as commercial teams. And there was one concentration sensor. The Sensorian set up a network of concentration sensors around the gas release platform. And then we also had 2 imaging technologies participate. And so our mobile ground teams, which were our vehicle teams, are all academic teams or a combination of academic groups. And they all drove in circles around the gas release site to get concentration measurements and then used Gaussian plume modeling. We also had the DTU team from Denmark use a tracer gas dispersion method. So they placed a tracer gas in the gas release site that was releasing continuously while the methane release was ongoing. And so they were using that in their modeling to get the emission rate. And then we also had the combination team where 4 different European universities or research groups came together and shared their data, which is pretty interesting and pretty cool. Finally, we had aircraft and satellite teams. The aircraft were both academic operators. There was the Swiss team from EMPA and University of Zurich that used remote sensing technology. And then there was the FAM team that flew in really low orbits around the gas release site. And if you look at this bottom photo, I don't know if y'all can see, but there's a pretty big plane that was just flying in circles around the test site right here. That's the best picture we could get. And then we also had one satellite participate, GSG-SAT, that's also remote sensing technology. And so each team was assigned 1 week of testing. The fixed sensors, except for the fixed sensors, which measured for either all 4 weeks or a 2 week campaign. And then also the satellite was tasked a couple of times each week. And so the number of measurements that each team got was varied. But a lot of this was due to just the operational constraints of the TADI test site. So a little bit about the TADI facility specifically. This was built for gas release testing. initially for development of technology with safety applications, but eventually expanding to measurement-focused systems as well. TADI is located in the south of France, in Lac, France, which is close to the Pyrenees, and it is part of a broader TotalEnergies research complex in that area. It's located on an active industrial site with other industrial operations going around all around it. So this is kind of having the aim of testing commercially ready and deployable systems that are able to work within the confines of operating on an industrial site. You know, there was some limitations on where drones could fly. There was limitations on like the aircraft, how low they could get to the ground, where you could place the sensors, which is something you find in like typical practice at a oil and gas facility. And this was the first time that the site was used for an independent and public study, although TotalEnergies has used it to develop and test their own technology over the past several years. So this is just another view, a top-down view of the TADI facility. You have the gas release platform in the center in red with the Sensorian network of sensors around it. The orange refers to the areas where the drones were able to fly. And then you also have the SLB and Sensia fixed sensor cameras located on a tank that was kind of up into the side. And then you can see there's a lot of other activity going around just in this part of the site, and then as well, kind of all around it. So there's a lot of stuff going on around the site that resulted in some constraints. And TADI was modeled after METEC in Colorado, and TADI and METEC have published joint protocols to be used at their facilities to try to begin to standardize the controlled release testing. So we focus on testing the quantification and detection abilities. And if we had to choose one technology to base the experiment around, we were thinking of mobile solutions. So the drones and the vehicles. And designing an experiment specifically for aircraft or for satellite or for fixed sensors would probably look different. But because we really wanted to test the drones and the vehicle teams, since that's where the bulk of the European measurement industry is today, that's what we were going for. And so with this in mind, we had 45-minute long releases, a daily schedule that was with the start and end of the release periods known to all the operators. There was a 15-minute break in between for plume dispersion as well. And this photo here is just showing you the like manual recording of the start times and ends. And in this case, when there were two drones, which drone was flying, because you could only have one drone flying at each time. And so while the start and end time of the release period were known, the location on the gas release platform and the emission rate were both blinded, as well as kind of the type of release. So we either just released some amount of methane or we had a zero release, so an intentional non-release of methane, which none of the participants were aware of. And we also had what we called a satellite scale release, which was coordinated with the satellite overpass. So this was somewhere in the range of 100 to 300 kilograms per hour, which is at the upper end of what TADI could do for a 45-minute long release. And this was only happened a couple times a week. This is an example of the data collection from the Swiss team from EMPA, University of Zurich. You can see here the plumes that they identified coming from the release site, and just an example of one type of data that were collected during this experiment. This is the example data collection from the FAM aircraft. So these circles on the left are showing the orbits that they flew around the TADI facility with the associated and concentration measurements that they were making. And you can see the peaks of the concentration on the right. And they had a variety of different instruments within their airplane. So that's why you can see multiple types of gas, but we're specifically interested in the methane one. So is the top peak that you can see there. And this is an example of the vehicle data that were collected. This is from the Heidelberg University team. They were driving essentially in circles around the test site during all of the releases and measuring concentration as well. And most of the vehicle teams had very similar data collection processes like this. And so, although we tried to make the data reporting process as standard as possible, there was still some variation in how the teams reported in their measurements. So, for each release period that the schedule they had, they explained if they took a measurement or not, and if so, did the quantification process fail during that release? And based on different explanations the teams provided for why the quantification status failed, we either assigned those estimates as zero estimates, so a release rate of 0 kilograms per hour. And this is, for an example, a team reported in that the quantification process failed, but the reason was because the concentration measurements were below their level of detection. We took that as the team telling us that they had a 0 kilogram per hour estimate for those measurements, but sometimes there were other reasons why the quantification failed, such as weather, wind, sensor malfunction, and we did not include those data points in our analysis. And we went through this process for each team with some level of customization for each team. And so I think it's noteworthy to mention that just the amount of data points that are filtered either by the participant themselves or by our own data processing pipelines. Like I mentioned before, this was due to equipment malfunction, low wind speeds, weather conditions. The Aramon team had one of their equipment needed not even show up when they were shipping it from Finland, so they had to throw out some of their measurements. The Heidelberg team has a operating condition for their a data quality check on the wind speeds. So for when wind speeds were below a certain threshold, they did not submit estimates. And then I think it's important to talk about the aircraft and satellite teams. Although a lot of the teams were impacted by weather, there was some rain that just prevented, all of the teams from measuring. The aircraft and satellite teams were especially hampered by the cloud conditions that were covering the site. So in particular, the satellite GHGSat was tasked 12 times, but they only could provide one measurement, which is kind of the main takeaway you can take from for the satellite team in this experiment, because you can't really conclude much about one measurement, but you can talk about the fact that they had 12 opportunities and could only take one. And this is spread across 4 different weeks in June and September, so different time of year as well. So getting into the results, the TADI facility has the capability to release very small amounts of gas with good precision, which makes testing the detection limits of these technologies quite interesting, I think. And in general, the ground deployed systems were able to detect very small emissions. So all vehicle, drone, and fixed ground sensor teams detected emissions below 1 kilogram per hour. And the rates of false negatives are generally higher than the false positive rates, which means teams skewed towards reporting false or teams skewed toward reporting like false negatives and didn't want to say there was an emission when there wasn't one in reality. Um, and again, you can note here the lower number of measurements that the aircraft and satellites submitted, and which just kind of speaks to the difficulty of deploying these types of technologies in the higher latitudes with more variable weather. So for some of the teams, we were able to produce probability of detection curves, which are shown here. You can see the number of releases and detection, the amount of releases or percentage of releases that they detected up until or under 30 kilograms per hour. Um, and for some of the teams, the probability of detection curves are shown in the blue lines on the graph. And so you can use these to estimate like a 90% probability of detection, a 50% probability of detection, whatever you want, which is helpful in determining detection limits. But keep in mind, these are specific to kind of the conditions that these measurements were conducted in. And we also had 4 teams that detected all of the non-zero releases. So we weren't even able to calculate a probability of detection curve. And so more testing with lower release rates would help to like test this and confirm this, but it also shows the sensitivity of the sensors and that in general, like especially the drones and the vehicles, they can detect like pretty well because there were some extremely low releases that they still were able to detect. And while detection was successful, the quantification accuracy varied pretty significantly between all of the teams. This table contains the slope and the R squared of the best fit linear regression between the reported and the true emission rates. Um, a slope of 1 is ideal, and a slope above 1 indicates overestimation on average, and a slope less than 1 means that on average the reported release rates were less than the true release rates. So there are top performers across all technology types. There were drones, vehicles, and aircraft, satellite, and fixed sensors that all performed pretty well. Um, but in general, the commercial operators tended to underestimate the releases, and there were some established academic research teams like the DTU and the Heidelberg University that performed quite well. So you can also visualize quantification ability in a parity chart, which is shown here. Again, the slope of 1 is ideal, which is the black line in the center. And most of the best fit lines fall below the parity line, which indicates like a tendency to underestimate the true release rate. What's also interesting here is you can see the duplicate measurements of all of the teams, which a lot of times is the teams that measured at the like concurrently at the same time. Or we also repeated release rates over the same week. So each team would see the same emission rate multiple times, which is quite interesting to see that just like the distribution for this one right here around like 290 kilograms per hour. There's just like such a wide variety of all of the estimates submitted by teams, but they're all they're all below the true release rate. And also in the table to the left, we looked at the both the percent of estimates that contained the true value within their uncertainty ranges. And I think there's only 4 teams that had 50% or higher of the true value within their certainty ranges. So 50% of estimates contain the true value. Um, and we also looked at the estimates that were within 50% of the true value. And that was a little bit higher. But again, just another way to think about the accuracy of these different systems in their quantification ability. So we also looked at the difference in performance when you included those high volume satellite scale releases, which were maybe like 2 to 4 a week, and when you didn't. And it's interesting because there's no one impact of the like higher volume releases on the quantification ability of the different sensors. So they both improved and worsened the quantification results. So the teams in red show, or the rows in red show the teams whose best fit linear regression slope, um, a proxy for average quantification ability, worsened when only looking at the smaller releases, which means their quantification of large scale releases helped them and resulted in like a better average performance. And the green lines are those that improved when only looking at smaller releases. Um, and There was one team who's the CCOPS team, their performance actually didn't change. And then the GSMA Aussie team actually didn't measure any releases above 100 kilograms per hour due to some scheduling issues. And what's interesting is the impact of these high volume releases changes depending on the technology group that you're looking at. So only one of the mobile ground teams, the drones and the vehicles, performed better when only releases less than 100 kilograms per hour were considered, while all the fixed sensors in the aircraft showed better quantification ability on smaller releases. So another way of looking at quantification ability is looking at like the total volume of methane that was released for each team and summing up all of the estimates that the team submitted. And so almost half of the participants quantified the total amount of emissions within their stated error intervals. And we had at least one team from each of the technology groups, one drone, two vans, one fixed sensor, one aircraft, and one satellite reach this milestone. And so this kind of highlights that while like the technology is capable on average, consistent accuracy across all conditions remains a hurdle for the industry. But if you're kind of looking at the general picture, and you want to sum up all of the emissions over time, which is a lot of the inventory work is on, a lot of these measurement or these technologies can actually do that within uncertainty ranges. But additionally, in some cases, the error bars are quite large, which indicates that participants could focus on reducing some of the uncertainty associated with their emissions measurements. So after looking at the results in the quantification performance, one of the questions that we had was if and how the environmental conditions were affecting kind of quantification ability. And we I want to quickly talk about kind of the inconsistency specifically of wind conditions throughout the 4 different testing weeks. There were really different winds. For example, during week 1, shown on the top here, you had pretty high winds and pretty consistent direction, like it was not shifting around. While during week 4, the wind conditions were really difficult. Especially like this release number 35 on the bottom right, consistently all below 2 meters per second. And I mean, the direction is shifting, which makes it really difficult to measure the plumes, especially for like concentration sensors that are, you have to kind of drive around or fly around and find the plume before you can measure it. And so one of the big takeaways to come out of this round of controlled release testing was the importance of wind to measure emissions effectively. And it's well established that measuring concentrations in low wind speeds is very difficult. And we saw the impact of that in our experiment. So the average quantification performance of all teams, so that means you put all of the measurements or all of the release estimates submitted by all of the teams into one bucket, and then divide up that into the different average wind speeds during the release. And when the wind speed was above 2 meters per second, the average quantification performance of all of the teams improved by a factor of around 2, which you can see on this graph visually, and the increase in slope of that best fit line increasing when the average wind speeds were above 2 meters per second. And we can't really go much deeper on this than the average wind speed across like all teams, but I think would be really interesting to test on a team by team basis, because obviously there's also different quantification performance between all of the teams. But it kind of solidifies the importance of having operational constraints while you're measuring. Like you shouldn't really go out and measure when wind speeds were below 2 meters per second, is kind of one thing that you can conclude from this analysis. And we also wanted to highlight the importance of taking quality wind measurements while deploying the emission measurement technology. So we had 3 participants uncover systematic errors within the sources of wind data that they were using after unblinding of the true release rates. So they all saw improvement in the quantification ability when using the LiDAR wind measurement system that was installed at TADI. And that wind data was provided during the unblinding. And you can see the improvement in these results and these white papers or publications that some of the teams have undertaken after they use different sources of wind data and saw like a transformation in their ability. But again, all of these are analyses were done after unblinding of the true results. And so one of the advantages of providing wind data in a controlled release study is you can check your measurements against our source. And the team that used the same wind LiDAR wind measurement system that was installed at TADI, they brought their own version of it and installed it for the week of their testing. That was one of the ones with the best performance. So investing in good sources of wind data is also pretty important, almost as important as the conditions during which you should operate. So in conclusion, while we can say that most of the ground deployed technologies that we've tested have mature detection capabilities, we still need more controlled release testing to determine the detection limits for aircraft and remote sensing technologies, especially at higher latitudes where the weather is more variable. And the gap between the quantification ability of different technologies is still present. And while there are systems that need improvement, there are also technologies of all types that are able to perform accurate measurements, especially when you're taking like a total emissions inventory view and looking at the uncertainty of the estimates as well. One of the big conclusions of these studies was the importance of winds, especially in highlighting the need for high quality wind data when quantifying emission rates. Our findings also support establishing conditions during which systems should measure, such as when average wind speeds are above 2 meters per second. And this also ties into the weather conditions playing an outsized role in this controlled release experiment, especially when compared to the other ones that my lab has done in Arizona, which is like essentially sunny and not cloudy all the time. And finally, just to ensure that methane emission measurements continue to be the gold standard in emissions reporting, more controlled release testing should continue to be conducted independently and at a global scale. Um, so with that work, as I talked about in the beginning, regular testing is important. And one of the benefits of having dedicated facilities like TADI and METEC is there's less operational overhead to spin up an experiment. And that's what we've been doing with our test site in Arizona, which has the capability for really high volume, high release rate, high emission rate releases. And so we've just finished a year-long test of satellites in Arizona. Fran Royland from my lab came and spoke about the initial results of this last spring, and is working on publishing the final results. And we're also soon to be starting a flare experiment where we take this gas release methane stack and we light it on fire. So if you have any questions about that as well, I can connect you with the person in my lab who is leading that experiment. So just a big thank you to the team at TADI, our sponsors at IMEO, and all of the teams who participated in this experiment. It was honestly super fun for me to meet everyone, go to be able to go to France, talk to both the companies and all of the other research groups who are working on this really important question. I have a paper under review that is available as a preprint. That focuses on the results of the commercial teams, and the academic team results should be available very shortly. And many of the teams have conducted their own post-unblinding analysis and have made these publicly available. So you can search for these white papers or refer to the references in my commercial teams paper. And a lot of them have done a lot of work in incorporating the results of these experiments into improving their methods. So it's pretty interesting and cool to see how the impact of these experiments are affecting the technology today. Um, so yeah, if anyone has any questions, would love to chat with you guys, and yeah, let me know if you have any questions.